Welcome to the debate. You know, when you go to a symphony, you don't just listen to the oboe.
Right, you'd miss the entire piece if you did that.
Exactly. You'd miss the harmony, the tension, the whole overarching architecture. But historically, in human biology and preventive medicine, we've kind of been forced to listen to just the soloists.
Yeah, the cardiologist looks exclusively at the EKG, while the endocrinologist focuses entirely on the continuous glucose monitor.
And the geneticist is only looking at the DNA. But today, we are experiencing a massive paradigm shift. We're now integrating artificial intelligence into global human biology on just an unprecedented scale.
We're talking about analyzing petabytes of multi-omics data, everything from continuous glucose monitors in the microbiome to retinal imaging and wearable behavioral data.
Right, which brings us to the central question we are exploring today. Does the sheer scale and architecture of multimodal AI represent a triumphant decoding of human biology that genuinely democratizes global health?
Or on the flip side, do the mathematical abstractions required to process all this data, combined with inherent systemic data biases, create a reductionist, fragile system, one that risks misinterpreting complex biology and exacerbating inequities?
Today, I will be arguing that AI's deep learning architectures successfully harmonize this biological chaos. I really believe it overcomes human cognitive limits to achieve predictive mastery.
And I'll be arguing that compressing high-dimensional biology into mathematical embeddings strips away vital context. Relying on skewed datasets risks deploying an AI colonialism that pathologizes variants and ultimately fails vulnerable populations.
So, to start, let me lay out my initial perspective. From my vantage point, artificial intelligence is quite literally the only tool capable of mapping the body's orchestra.
How so?
Well, human cognition, no matter how brilliant the physician, it fundamentally fails when a disease doesn't just show up on one test. It fails when the disease manifests as, subtle shifts across thousands of interacting biomarkers.
Right. The sheer data volume is staggering.
Exactly. Take multimodal transformers, for instance. This is similar to the architecture behind large language models, but instead of predicting the next word, it translates different biological languages.
Fusing different modalities together?
Yes. We now have models that can fuse a retinal image, like a picture of the back of your eye, with your genomic data, specifically single nucleotide polymorphisms, or SNPs.
Ah, right.
By cross-referencing the structural layout of those tiny blood vessels in your eye with specific genetic typos in your DNA, the AI predicts diabetic retinopathy 15% better than traditional clinical methods. It sees the invisible correlations.
That is a significant improvement, I'll admit.
And we're doing this at a global scale. Look at DeepMind's AlphaMints. It doesn't just look at one gene. It cross-references 71 million possible missense variants.
Those are the mutations where a single wrong building block changes a protein shape, right?
Exactly. And it flags which ones are likely to cause disease. This isn't just theoretical modeling. It is active democratization of healthcare. Because of this cloud-based integration, an under-resourced clinic in Mumbai can plug into that exact same model.
And match the predictive outcomes of an elite Western hospital.
Exactly. The AI finds the hidden biological harmony and standardizes that insight globally.
I hear the optimism there, and, the Mumbai example sounds wonderful on paper. But processing volume does not equal biological understanding.
Okay, walk me through your thinking.
I come at it from a completely different way. AI relies on algorithms that fundamentally compress and abstract reality in order to function. In data science, we talk about the curse of dimensionality.
Right, when your variables vastly outnumber your samples.
Precisely. Imagine you are trying to solve a medical mystery. You only have 100 patients, but you've sequenced their microbiomes. That means you have tens of thousands of bacteria biomarkers.
Plus their genetics, metabolic panels, all of it.
Exactly. You have 10 billion clues for 100 suspects. So to force this massive, chaotic data into a usable predictive model, AI relies on dimensionality reduction techniques.
Like principal component analysis or PCA and autoencoders.
Right. Tools designed to squash thousands of variables down to a handful of mathematical summaries. That mathematical flattening loses critical nonlinear biological context.
But doesn't it distill the noise down to the essential, actionable signals?
It's not just noise you're cutting, though. Furthermore, we are building this massive global infrastructure on a house of cards. The training data powering these global models is roughly 80% Caucasian skewed.
Which is a known issue, yes.
But if you feed a fundamentally biased, Western-centric dataset into a highly abstracted algorithm, its predictions are going to fail, and they're going to fail spectacularly on diverse global populations.
I want to spend some time on that concept of mathematical flattening. I have to admit, when I first looked at how an autoencoder actually works, it felt like magic.
Taking a high-definition image and forcing it through a bottleneck.
Right. You take a massive, high-definition image of someone's biology, force it through a tiny mathematical bottleneck, and the machine rebuilds the patterns on the other side. But you view that pre-processing pipeline as inherently destructive.
They have to be destructive. That is their mathematical function. Think about it like a topological map. Human biology is the Alps.
Okay, I like that analogy.
It is immensely complex, full of jagged peaks, deep valleys, and incredibly intricate localized microclimates. When you use an autoencoder or PCA to compress petabytes of multiomics data into a latent space, you're flattening it.
You mean turning it into a two-dimensional line drawing?
Exactly. You lose the elevation, you lose the microclimates.
I see the visual you're painting, but even on a two-dimensional map, you retain the relative distances between the landmarks. A map of the Alps still tells you exactly how to navigate from one peak to another, which is what a clinician needs.
You retain an approximation of distance, yes. But in that approximation, spurious patterns easily arise because the map lacks depth. We've actually seen this happen in the real world.
Are you thinking of the Delhi healthcare datasets?
Yes, where unsupervised algorithms confidently found what looked like a novel, deeply complex proteomic signature for a new respiratory disease pathway. The AI flagged it as a massive biological discovery.
But it turned out to be something else entirely.
Right. When researchers actually dug into the biological mechanism, it wasn't a disease pathway at all. The AI was just tracking the mathematical shadow of urban air pollution.
Ah, the heavy metals and particulate matter in the air.
Exactly. They were mimicking an inflammatory disease signal in the blood. The machine doesn't know the difference between an endogenous biological mechanism and an environmental confounder. It just knows math.
Well, I'm not convinced by that line of reasoning because you're treating AI as if it's strictly a compression algorithm, like we're just zipping a file to save space on a hard drive.
But at its core, isn't it?
Not entirely. Deep learning excels at mapping interdependence. It doesn't just flatten the terrain of the Alps, it maps the hidden tectonic fault lines beneath the mountains. This is exactly where graph neural networks, or GNNs, change the paradigm.
Modeling nodes and edges, you mean?
Exactly. The organs, the metabolites, or the specific bacteria are the nodes, and the literal biological conversations happening between them are the edges. Look at Europe's MetaHit consortium.
They use GNNs for the microbiome, right?
Yes, they utilize GNNs to predict gut dysbiosis, which is a severe microbiome imbalance in 90% of cases. And they didn't do it by flattening the data. They did it by mapping the complex cascade of interactions.
Okay, so mapping the specific bacterial interactions.
Right. The model recognized that a specific bacterium, Bifidobacterium, actively feeds another bacterium called Akkermansia. The AI saw that when that feeding happens, it triggers the production of short-chain fatty acids,
which creates a massive anti-inflammatory effect in the host's gut lining.
Exactly. The AI captured the entire causal cascade. Furthermore, if we look at the self-attention mechanisms inside multimodal transformers, they do the exact opposite of erasing context.
How so?
Self-attention weighs the importance of distant variables against each other. It can look at a glucose spike on a monitor at 8 a.m. and mathematically connect it to a ketone rhythm occurring 12 hours later. It preserves long-range biological dependencies.
Well, I will grant you that graph neural networks offer a vastly more sophisticated topology than basic PCA. They do map relationships beautifully.
Glad we agree on that point.
But your MetaHit example actually perfectly highlights the structural problem we face. MetaHit is a European consortium. The network models you are praising are incredibly precise, but we have to ask whose network we are mapping.
You're bringing it back to the data diversity issue.
Looking at a global data landscape where 80% of genomic data is Caucasian skewed. Our bacterial DNA databases are roughly 90% skewed toward gram-negative bacteria, largely due to historical sampling biases.
The data diversity problem is real, and the scientific community is well aware of it.
But it's more than just a hurdle, it's a systemic failure. If we export these specific models, we are engaging in a form of AI colonialism.
That's a strong term. AI colonialism?
It fits, though. We have Western algorithms trained almost exclusively on Western physiologies, metabolisms, and ultra-processed diets, dictating health policy and diagnostics in the global South.
But we're working on that.
We've already seen it fail in practice. AI metabolic models have consistently underdiagnosed lean diabetics. This is a phenotype very common in South Asian populations, where patients develop severe insulin resistance without being overweight.
Right, because the algorithm expects a high BMI.
Exactly. Because the Western training data rigidly associates insulin resistance with high BMI and visceral fat, the algorithm learns that rule. It looks at a South Asian patient with a low BMI, applies the Western rule, and completely misses the diabetes.
But this is precisely where the architecture of modern AI is providing the structural solution to those data silos. We aren't just taking an algorithm trained in Boston and blindly exporting it to Bangalore anymore.
You're talking about federated learning.
Yes, we are using federated learning to build global equity without centralizing data.
But federated learning just keeps the data localized on the hospital's own servers for privacy, which is good. But it doesn't magically create data that isn't there.
It does much more than just protect privacy, though. Federated learning is the great equalizer. Instead of moving the diverse data to a central algorithm, we move the algorithm to the diverse data.
So the hospitals train the model locally?
Exactly. Hospitals train the model locally on their own unique populations. Then only the mathematical learnings, the updated weights and gradients, are shared back to the central model. The raw data never leaves the local server.
Okay, but how is this working in practice?
Look at what is happening in Brazil right now. The Fiocruz Research Institution is deploying federated learning across the SUS public health system. That is 50 million patient records.
That's a massive data set.
It is. They're predicting polycystic ovary syndrome, or PCOS, and insulin resistance across incredibly diverse Latin American ancestries. And because the raw data never moves, they are doing this in total compliance with Brazil's strict LGBT privacy laws.
Right, the data protection laws.
And in regions where the data is genuinely sparse, AI is actively solving resource gaps. Take Rwanda. We have zipline drones delivering malaria nets and medical supplies based entirely on AI forecasts.
Using weather and genomic data, right?
Yes. The AI digests incoming humidity and temperature data from weather satellites, cross-references it with the known genomic breeding cycles of local mosquito populations, and predicts exactly where a malaria outbreak will spike next week.
So they preemptively deliver the supplies.
Exactly. The drones deliver the nets to those specific villages before the mosquitoes even hatch. That is real-world localized predictive power.
That's a compelling argument, but have you considered the mathematical sleight of hand that the industry is using to patch the data gaps you just mentioned?
What do you mean?
You brought up sparse data. Often, the tech industry solution to missing genomic diversity isn't to actually go out and sequence more diverse populations. Instead, they use generative adversarial networks, or GANs, to create synthetic data.
Synthetic data augmentation is a heavily vetted mathematical technique, though. It's used constantly to balance out training sets so the model doesn't overfit to the majority class.
Let's explain what a GAN actually does. It pits two neural networks against each other. One generates fake patient profiles, and the other tries to guess if they are real or fake, until the fake data is indistinguishable from the real data.
Right, that's the standard adversarial process.
But applying this to biology is a mathematical band-aid over a systemic absence of real representation. If you do not have enough African genomic profiles in your database, you cannot just have an algorithm hallucinate them.
It's not hallucinating, it's extrapolating based on statistical parameters.
But it's simulating diversity rather than studying actual lived human biology. It assumes we already know the parameters of the biological variants we are missing. I mean, that is scientifically arrogant.
Well, I think arrogant is a pretty strong word to apply to a transitional methodology. I would frame it more as iterative improvement.
Iterative improvement with fake data?
Is synthetic data a perfect substitute for real-world sequencing? No, of course not. But combined with massive global initiatives like the H3 Africa Consortium, which is actively sequencing indigenous tribal genomics across the continent, the models are rapidly becoming more representative.
We'll see how representative they actually get.
We have to look at the clinical outcomes we are achieving right now, today. By shifting medicine from reactive firefighting to predictive prevention, AI has massive potential.
In terms of mortality reduction?
Yes, the Lancet estimates that predictive AI could avert up to 40% of preventable deaths globally. Think about what that actually means in practice.
It means a lot, obviously, if the predictions are accurate, and more importantly, if they are actionable for the patient.
And they are actionable. Look at Virta Health. They are using AI to analyze continuous glucose monitor data and complex metabolic profiles, and they are successfully reversing 60% of insulin resistance cases.
That's an impressive number. But how are they doing it?
Not with drugs, but through highly personalized, real-time ketogenic coaching driven by the AI's analysis of what specifically spikes that individual patient's blood sugar.
Okay, that's one targeted use case.
But look at the public health scale too. The UK's National Health Service has deployed AI risk engines across general practices. The AI scans the patient histories and prioritizes exactly who needs statins or immediate lifestyle interventions.
Aiming to prevent cardiovascular events.
Exactly, aiming to prevent roughly 100,000 cardiovascular events a year. And to your earlier point about the algorithm being a black box, we now have sophisticated explainability tools like LIME and SHAP.
Which are highly contested in the medical data community, by the way.
But they work. Tools like SHAP essentially reverse engineer the AI's math. They play a game of hypothetical subtraction. The AI doesn't just spit out a generic risk score, it isolates the why.
By highlighting specific variables.
Right. It tells the clinician, hey, this patient is at risk of a cardiac event specifically because of a combination of gut dysbiosis and a high LDL cholesterol edge. It highlights the exact variables that triggered the alarm. That is how you build clinician trust.
I'm sorry, but I just don't buy that the explainability problem is solved. SHAP values are approximations. They just tell you which feature the model mathematically weighed heavily to make its guess.
That's essentially the mechanism, yes.
But in a complex, high-dimensional, multimodal fusion, where the AI is combining genetics, microbiome, and wearables, the actual underlying biological mechanism often remains a complete black box to the physician. The true why is still hidden.
But let me ask you this. If you're a doctor looking at this data, and the prediction reliably prevents a patient from having a massive heart attack, do you fundamentally need to understand the calculus of the 5,000 dimensional latent space?
You absolutely do when the model is wrong. And that brings up the profound danger of what I call probabilistic pathologizing.
Probabilistic pathologizing?
Yes. Let's say an unsupervised clustering algorithm looks at a patient's multi-omics profile. It identifies a mathematical pattern that it labels as a buildup of silent fibrosis in the liver.
Okay.
The patient has 0 symptoms, they feel perfectly fine, but now they are flagged in the system as a high-risk patient. This risks immense psychological anxiety and severe over-medicalization.
But prevention inherently relies on acting before symptoms appear. That is the entire fundamental philosophy of early detection.
Yes, but not all flagged risks require an aggressive intervention. A mild hyperinsulinemia spike or a slight deviation in an inflammatory cytokine panel might just be the body's temporary homeostatic adjustment.
Like responding to a stressful week or a minor infection.
Exactly. It does not automatically require a lifelong pharmaceutical intervention, like putting the patient on a GLP-1 agonist. When we allow an algorithm to redefine what constitutes a disease state based entirely on mathematical clusters, rather than actual clinical suffering, we risk turning perfectly healthy people into lifelong patients.
That implies the AI is operating in a vacuum, though, making prescribing decisions on its own, which it isn't. The AI flags the risk, and the physician contextualizes it with the patient sitting in front of them.
Do they always, though?
We aren't replacing the doctor's judgment. We are giving them a significantly sharper lens to look through.
Or we are giving them an absolute avalanche of probabilistic alerts that forces them to practice defensive medicine.
Because they don't want to ignore the algorithm.
Right, if the machine's dashboard flashes red and says high risk for cardiac event, what doctor is going to ignore that? Even if their years of clinical intuition tell them the patient is fine, they will prescribe the statin just to avoid the liability of the algorithm being right.
Look, I understand the concern about alert fatigue and defensive medicine. I really do. But I think we have to weigh that risk against the staggering reality of our current global health burden.
Which is immense, undeniably.
We have over 540 million people globally facing diabetes. We have chronic, metabolic diseases crippling healthcare infrastructures from the US to India. So as we look to summarize our positions today, my stance remains firm.
Go ahead.
Despite the very real challenges of data bias and interpretability, AI's ability to fuse these massive multimodal streams, from smartwatches to 16S RNS sequencing of the gut, is the only viable path forward.
You don't think traditional methods have a place?
Traditional, hypothesis-driven, one-variable-at-a-time biology simply cannot scale to manage the exploding burden of chronic disease. By harmonizing this multi-omics data, we are moving toward a future of true, global predictive health.
And my position is that as we build that future, we must remain intensely vigilant against algorithmic hubris. We cannot allow complex, nonlinear human biology to be stripped of its vital context and lost in mathematical latent spaces.
Which is a valid caution.
More importantly, we must ensure that our predictive models do not inadvertently weaponize structurally biased data against the very vulnerable global populations they are supposed to help. Efficiency and processing scale are incredible tools, but they are not substitutes for equity and biological truth.
I will say we certainly agree on a fundamental premise here. Traditional biology is insufficient for the sheer scale of modern health data. The magnitude of decoding what scientists call the microbial majority, mapping these global metabolic networks, it absolutely requires immense computational power.
Agreed. There is no going back to the era of just the stethoscope and the singular blood test.
Right.
And I think we also converge on the vital need for rigorous structural frameworks, things like the World Health Organization's Global Ethics Framework for AI, and the implementation of dynamic, continuous patient consent.
Essential guardrails.
Exactly. These aren't just bureaucratic red tape. They are the essential, structural guardrails that will ultimately determine whether this multi-omics technology heals or harms.
Absolutely. And the field is moving incredibly fast. As emerging technologies mature, like quantum AI simulations that could eventually model complex organ failure cascades in real time without the dimensionality constraints of classical computing,
Or edge computing wearables that process all of this dense data entirely on the device without ever compromising a patient's privacy.
exactly. There is far more to explore in how we map the human system.
There is. The map is expanding rapidly, but we just have to remember to keep our eyes on the actual lived territory.
Well said. We will leave it to our listeners to weigh the incredible promise of global predictive health against the profound structural perils of algorithmic abstraction. Because ultimately, we are all part of this immensely complex biological symphony. And the question remains whether the machine can truly hear the music. We'll see you next time.